introduce and to welcome all of you to this event on Aaai 2022 at FBK. This event is very important for different reasons. First, we have three papers Aaai that, as you probably know, together with Aaai, is the most important, the most prestigious conference in artificial intelligence. And this should remember us where we come from. In the 80s, Istituto Trentino di Cultura, I say this also for the younger people that youngest people may don't know, Istituto Trentino Cultura was the former name of FBK, launched IRST, Istituto per la Ricerca Scientifica e Tecnologica, Institute for Scientific and Technological Research, with the aim, with the goal to do research in artificial intelligence. In these 40 years, we have been at the forefront of research in many different fields in AI. And we have been recognized, FBK has been recognized, IRST and then FBK, we have been recognized as one of the best research centers in AI all over the world. Then there is a second reason, and I remember a long time ago, more than 20 years ago, because I believe it was 2001, we had 3 papers at Aaai. Aaai is the other conference, together with Aaai, that is the most important conference in artificial intelligence. And at the time, Oliviero Stock, he was director of IRST. Without doubt, the best director that we had at FBK. He was very impressed. He organized something exactly the same as today. So after 20 years, we are here again to celebrate this kind of event, and this is very nice. Then another reason I'm very happy about this event is because we will have 3 presentations given by PhD students, young researchers, and so I'm very happy because the PhD students and young researchers are the future of FBK. But we have also to remember that these young researchers, PhD students, they have behind senior people that have made, still are making FBK famous researchers. In this case, like Alessandro Cimatti, Chiara Ghidini, and Luciano Serafini. So it's very nice to have young researchers that will be the future of FBK, but also followed by very important, outstanding researchers recognized all over the world. And after this presentation, I hope that this event will be also a stimulus for all the young researchers to submit papers to the most important conference in artificial intelligence and to have, of course, those papers accepted. After the 3 presentations, we will have Oliviero introducing Luciano Serafini, celebrating his nomination to Aaai Fellow. And just to remember how important is this kind of nomination, let me just say, when you get this certificate, you get the motivation. The motivation is for pioneering work in the field of artificial intelligence and outstanding service to the AI community. So this is a very important. Oliviero will introduce Luciano. Oliviero was the first, a long time ago, to be nominated as Aaai Fellow. Then we'll have the celebration, another kind of celebration of the prize of the award by Carlo Straparava, again at Aaai for a paper, an old paper. In 2006, it has been the most influential paper at Aaai. And I believe that this is probably the most prestigious award that a paper can have at a top conference like Aaai. And last but not least, I'd like really to thank Chiara, because Chiara had the idea to have this event, organize all this event, and without her, we wouldn't have this event. That is very important because we have to celebrate good things. So I believe that I'm very happy to join me in a warm welcome to all the young research and PhD student speakers and all the senior researchers that I have just mentioned. I leave the word to Chiara, so thank you very much.
So thank you, Paolo, and thank you all for being, here. Can you hear me nicely? No? Okay. So there is a small change in the program. So we swapped basically Luciano's and Sagra's presentation with the last one, who will be done by Mauro, and Ivan will be also present in a virtual manner, because unfortunately Luciano has to leave earlier, and therefore we will collapse basically or concatenate his presentation and the celebration of Luciano as a Aaai Fellow. And now we can start with the presentation of these three papers. I'm also really happy because they are papers that tackle foundational aspects of research. So they are important, they highlight directions, important directions. They are really, I mean, they cover mainstream topics that we work on here at FBK, and they are also very diverse. So I think they give us, and they are an opportunity also for young people here to listen to the breadth, let's say, of research we do here in FBK. So I would leave the floor to Stefan Pankovic, who will start the first presentation. I remember the speakers, I mean the presenters, they have 20 minutes plus 5 minutes questions. We will have to keep, let's say, the time and the agenda strict because of also of Luciano's timeline. And yes, the floor is yours. You will present a paper on deciding unsolvability in temporal planning under action, non-self-overlapping.
Thank you. Okay, so hello everyone, I am Stefan Pankovic, and I will be presenting the paper that I wrote with Andrea Michele and Alessandro Cimatti at the Embedded Systems Unit, called Deciding Unsolvability in Temporal Planning Under Action Non Self-Overlapping. So the context is Aaai planning, where the objective is to design a planner which receives in input a system specification, which is a formal model of the reality, together with a description of how a set of available actions change its state. It receives in input an initial configuration of that system and a goal that needs to be reached. And the planner must be able to automatically synthesize a plan, which is a course of actions that brings the system from its initial configuration to its goal state. Now, in classical planning, we assume that all the actions are deterministic and instantaneous, and that plans are simply sequences of actions. But in this paper, we are focusing on temporal planning, where temporal aspects such as deadlines, synchronization between actions, or the precise timing of events are modeled explicitly. And in this case, plans are no longer simply sequences of actions, but they are schedules of actions, where for every action, we need to specify its starting time, its duration, and we can also have several actions running in parallel. So here in the picture below, you can see an example plan for the match seller domain, where in order to reach the final goal at the end, you need to apply the mend fuse action for each fuse F in the problem, but the mend fuse action requires that during its entire execution, the light must be switched on. So you need to run the light match and mend fuse actions in parallel in order to reach the final goal at the end. Now, we say that an algorithm for solving a temporal planning problem is a decision procedure if, when it receives in input a solvable problem, it eventually returns a valid solution plan. And when it receives in input an unsolvable problem, it eventually terminates, stating that no solution exists. Now, having a decision procedure for temporal planning can have several important applications. For example, when doing optimal temporal planning, a typical way to proceed is to progressively tighten the problem constraints and try to solve the resulting problems in order to obtain more optimized plans at each step. But clearly, if these constraints are tightened too much, then the problem may become unsolvable, and a decision procedure is guaranteed to detect that. Another important application is as a debugging technique to spot errors during the modeling that make the problem unsolvable, and a decision procedure can also help detect unsolvability in that case. And also in oversubscription planning, where you have a set of mandatory goals and a set of optional goals, and you want to include as many optional goals as possible in the problem while keeping it solvable. So in the literature, several temporal planners have been proposed that are able to find plans efficiently in a variety of domains. However, none of these planners is a decision procedure, and in fact, most of them are semi-decision procedures, which are guaranteed to find a plan eventually when they are given a solvable problem, but they are not guaranteed to terminate and prove unsolvability when they are given unsolvable problems. And it was recently proved in 2020 by Gigante et al. In this theoretical paper that the temporal planning problem over dense time is in general undecidable. However, under the assumption of action non-self-overlapping, which means that you do not allow two instances of the same ground action to run in parallel, then the temporal planning problem becomes p-space complete. And they showed this by presenting a reduction from the temporal planning problem to the reachability problem in a timed automaton. However, in the literature so far, no practical planners have been proposed that are able to prove that a given problem is unsolvable in the general case, under the assumption of action non-self-overlapping. So the contributions of our paper are the following. We proposed two novel decision procedures for temporal planning under the assumption of action non-self-overlapping. The first one is a reduction to symbolic model checking of time transition systems that works by encoding the temporal planning problem into an XMV model with clocks, while the second one performs a native heuristic search through the state space of the problem using difference-bound matrices to handle temporal constraints. And we also implemented both of these techniques, and we conducted an experimental evaluation comparing them with state-of-the-art planners on domains taken from the literature. So now I will start by presenting the first approach, which translates a temporal planning problem into an XMV model with clocks, and then you can apply model checking algorithms on the resulting time transition system to verify it. So given a planning problem P, which is described by this tuple, where F is the set of fluents or variables, and we restrict these variables to be either Boolean or bounded integers, otherwise the problem becomes undecidable. T is the set of timed initial literals, which are global effects happening at specific points in time relative to the start of the plan. A is a set of actions, and G is the set of goals. And given this temporal planning problem P, the variables of the XMV encoding are a set of fluent variables, one for each fluent or variable in F, a set of Boolean running variables, one for each action in A, and these are used to indicate whether the current action is, whether an action is currently running or not. A clock variable, one for each action, which are used to indicate whether the time since the action was last started. A global clock variable, which indicates the time since the plan started. And finally, a set of Boolean count variables, one for every event in P. And these variables are set to true when that event is applied. And they're basically used to make sure that we do not skip any event that was scheduled. Now, the transition relation is described symbolically using a set of constraints. And these constraints restrict the values that variables take in the next state, given the value of variables in the current state. So here, for example, you see how we model the start of an action. We say that if an action is not running, and in the next state it is running, which means that we started, then we reset the clock of that action to 0, and we set to false all the count variables associated to events of that action. So all these events now need to be applied, and they are scheduled as soon as we start that action. To model the end of an action, we say that if an action is running, and in the next state it is not, so we end it, then we check that the clock of the action satisfies the duration constraints of the action, and that all the count variables associated to events of that action are true. So we make sure that we do not skip an event. To model the application of an action effect happening at time k after the start of an action, we say that if an action is running and the clock of the action is equal to k, Then in the next state, we change the value of the fluent according to the effect, and we set to true the count variable associated to that effect. And the same for the condition. So if the action is running and the clock is equal to k, we check that the condition phi holds, and then in the next state, we set the count variable associated to that event to true. And we have other constraints which make up the transition relation and are described in the paper. Now, the goal state is a state in which the goal condition holds, no action is running, and all the timed initial literals and intermediate goals have been applied. And to model the goal condition, we specify an invariant property, which is the negation of the goal condition. And in this way, if the model checking algorithm finds a trace which violates this invariant property, then that trace corresponds to a solution plan for the original temporal planning problem. And we can prove that this approach is a decision procedure because the time transition system that is obtained by these constraints is analogous to the timed automaton that was used to prove the space completeness of temporal planning. And also, the model checking of this invariant property is analogous to the reachability problem in that timed automaton. So this concludes my overview of the first approach, and now I will move on to the second one, where we perform a native heuristic search through the state space of the problem using difference-bound matrices to handle temporal constraints. Now, a difference-bound matrix, or DBM, is a data structure that is typically used in the context of timed automata to represent clock zones, which are conjunctions of clock constraints. So basically, you can think of a clock zone as representing the set of all possible assignments for the clock variables that you have. And these constraints are of these two forms, so you can have a clock Ci less than or equal to an integer k, which can also be negative, and in that case you have a lower bound to the clock variable. And you can also have upper and lower bounds to differences of clock variables. And a DBM is typically represented as a matrix where you have all the clocks on the rows and all the clocks on the columns, and then on the diagonal entries you have the first type of constraints, while on all the other entries, ij, you have the constraints of the second type. And very importantly, a DBM is a canonical representation of a clock zone, meaning that equivalent sets of constraints produce the same DBM. Now, back to our setting of temporal planning. So we again associate a clock variable to each action, which represents the time since the action was last started. And then, during state space exploration, we associate to each state a DBM, which represents the current temporal constraints in that state. And when we switch from one state to another, we perform the necessary operations on the DBM to update the temporal constraints. So here in the picture, you can see an example of a partial plan that we are constructing as we are exploring the state space. And below, you can see all the DBMs which are associated to these states. So here you can see that at the beginning, we have the 0 DBM, where all the clock variables are equal to 0. Then what we do is we wait some time, and then we start action A. And to reflect this in the DBM, what we do is we first perform an up operation, which basically removes all the upper bounds from the clock constraints, and this models a time elapse. And then we reset the clock of action A to 0 as we start action A. And when we end action A, we again perform a time elapse, and then we intersect to the DBM the duration constraint of action A, in this case stating that the clock of action A must be equal to 2. And so on, and here at the end you can see that when we end action B, which has a duration between 5 and 7, we intersect to the DBM the constraint stating that the clock of action B must be between 5 and 7. And a very important operation of DBM is subsumption checking, which allows one to check whether the time region represented by a DBM is the subset of the time region represented by another DBM. And as we will see later, this is crucial in order to obtain a decision procedure. So the algorithm that we proposed is called CTP, which stands for Complete Temporal Planner. And the state is represented by the following tuple, where mu is the classical part of the state, so the set of assignments to all the fluent variables, which again here we restrict to be Boolean or bounded integers. Delta is the set of currently active durative conditions, which need to be enforced in this state. Lambda is an agenda on future commitments, which basically contains for each running action the list of events that still need to be applied for that action. And sigma is a DBM, which represents the current temporal constraints in this state. Now, given a state, we can generate its successors with the following successor function. So from a state S, we can either start a new action, and when we start a new action, we insert into the agenda lambda all the events of that action, and in the DBM sigma, we reset the clock of action A to 0. When we apply an event of an action, we change the assignment in the fluent, in the part mu of the state. If that event is an effect, we remove that event from the agenda lambda, and we intersect to the DBM the constraint stating that the clock of the action to which that event belongs must be equal to the timing of that event. And finally, we can perform a time elapse, and a time elapse keeps the discrete part of the state unchanged and performs an up operation on the DBM sigma. Now, we have proved that the state space that is generated by this successor function is finite, basically because the discrete part of the state is finite, and also the zone graphs of the DBM can be made finite through appropriate normalization operations, as is typically done with timed automata. And then the subsumption checking operation of DBMs that I mentioned earlier allows us to prune a lot during state space exploration, because if we reach a state that has the same discrete part of a state that we already visited and whose DBM is subsumed by the DBM of that state, then we can prune the search there, because all the states that we can reach from that state can also be reached from the state that has the same discrete part but a bigger DBM. And finally, we have proved that there is a bisimulation relation between the search that is done by this algorithm in this state space and the reachability that is performed in a timed automaton that was used to prove p-space completeness of temporal planning. And this allows us to conclude that this algorithm is a decision procedure, and even when given an unsolvable problem, it is guaranteed to explore the entire state space, does not find a valid solution plan, and therefore can state that the problem is unsolvable. Now, we implemented both of these approaches in C++, and they support a significant fragment of the animal language, which in addition to the functionality supported by PDDL, also allows one to specify intermediate conditions and effects, which are effects happening at arbitrary points in time during the execution of an action. And we also implemented an optimized Duple encoding of the timed automaton that was used to prove p-space completeness of temporal planning, and we use this as a baseline for our unsolvable benchmarks. In the experimental setup, we used both solvable and unsolvable benchmarks. For the solvable case, we took some of them from the IPC temporal track and some from industrial inspired domains, while for the unsolvable case, we took some of the solvable instances and then we made them unsolvable. For example, by adding an infeasible battery requirement or requiring an impossible synchronization of operations or making too narrow time windows. So here you can see the cactus plot comparing our approaches with state-of-the-art approaches on unsolvable benchmarks. And on the right, you can see the number of instances which were solved by all these planners. And here by solved, I mean which are proved to be unsolvable. And you can see that state-of-the-art planners like TPAC, FTP, and Optic are solve only very few instances and are not designed to handle unsolvable benchmarks in general. And also these instances that they are able to solve, they're able to solve them because their incomplete heuristic is able to eventually detect unsolvability. On the other hand, our approaches perform really well. So here in the cactus plot, you can see in yellow the NuXMV approach, which solves the highest number of instances, followed by CTP in blue, and both outperform the UPAL encoding in black. And here in red, you can see the virtual best solver, which takes the best solver for each instance. And this solver is better than NuXMV, and this shows that there is some complementarity between our approaches. And this is further shown in the scatter plots comparing them. So here on the left, you can see the scatter plot comparing CTP and NuXMV, and you can see how complementary they are. While on the right, you can see that CTP dominates the UPAL encoding. And finally, in this table, you can see the overall results. And in the first row, you can see the results on the solvable instances. And here you can see that the model checking approaches like UPAL and NuXMV perform poorly with respect to the state-of-the-art on solvable benchmarks. But the CTP approach, which here solves 390 instances, is competitive with the state-of-the-art. And this is mainly because in CTP, we do not do a compilation-based approach, but we solve the planning problem natively. And then we can employ a heuristic during state space exploration, which allows one to find solution plans much more quickly on solvable instances. So to conclude, we presented the first techniques, one compilation-based and one native search for temporal planning under action on self-overlapping that guarantee termination. We implemented them in C++, and they support a significant fragment of the animal language. And we conducted an experimental evaluation, which showed that NuXMV and CTP outperformed by far the other approaches on the unsolvable benchmarks, while CTP also remains competitive with the state-of-the-art on solvable instances. And in the future, we plan to investigate the complementarity between CTP and FTP, which are very similar but fundamentally differ in the way in which they handle temporal constraints, where CTP uses difference-bound matrices while FTP simple temporal networks. We plan to use CTP for optimal temporal planning and to use the NuXMV and Drupal encodings for domain and problem validation. So that's all from me, and thank you very much for listening. Yes?
And then you find a counterexample in some way. So in this sense, in your future work, you mentioned the idea to extend the work for optimizing. Do you think you need to change everything, or you could do some way keeping this kind of approach?
Yeah, so here the preliminary idea that we had with these approaches was to do a sort of, let's say, binary search, where you like, for example, if you want to optimize the battery consumption, you put a constraint on the battery requirement and you progressively tighten it. The problem was that if you didn't have a decision procedure, if you make the problem unsolvable, then the planner would not terminate, but you wouldn't be able to distinguish the case in which whether the problem is too difficult to solve or whether it is unsolvable. And with a decision procedure, which is guaranteed eventually to find to prove that it is unsolvable, you can do such binary search and find a point where the plan is that is produced is optimal.
Okay, there is a question here.
So I'm really naive about planning, but at some point you mentioned that your decision procedure explores all solutions. So at some point it will terminate. So I just want to understand, when you do the experimental evaluation, what is happening when it is not terminating? So on one hand, I understand it provably terminates, and in the experiment it does not sometimes. So what is changing?
When it does not terminate, it simply means that the state space is too big. Okay. And we set, on the experiments that we did, we set a time limit of 30 minutes, after which we killed the program. And if you increase the number of instances in your domain, then the state space grows, and sometimes it does not terminate.
Other questions? So if I can, I have two questions, more curiosities than actual technical questions. The first one is about your motivation. If I understood correctly, I mean, I understand in which sense it helps debugging, because if it is a no, it answers no. But you don't, if I understood correctly, you don't have any hint on where the problem is. Or yes, or can you use it also to support, let's say, the refinement of your specifications?
So when I mentioned as an application, as a debugging technique, what I was thinking about is that suppose you're modeling a problem and you make a mistake somewhere, and with that the problem is infeasible. But when you try to solve it with a planner, for example, if you use a planner which is not a decision procedure, you launch it and you see that it does not terminate. And then you are not sure whether it is because the problem is too complicated and it cannot be solved by this planner, or because it is infeasible. And if it is able to find that there is no solution, then that could be if you know that your model should have a solution, then that is an indication that there is a problem somewhere in your model.
Okay, but then you have to look at.
Yes.
Say manually.
Yes.
Okay. The second question is related with your starting point. So can you give me a hint of why dropping the non-overlapping constraint makes the problem then more difficult?
Yes.
I mean,
so
incomplete?
This was.
I mean, basically the Gigante results.
Yes. So basically. In the paper by Gigante et al., they proved that under the assumption of action non-self-overlapping, the problem is p-space complete because it can be reduced to a reachability problem in a timed automaton. If you allow actions to self-overlap, then the problem can be reduced to a tiling problem, which is known to be undecidable. And in our case, where do we use exactly this fact of action non-self-overlapping? We use it when we define the clock variables. So here, when we assume that there is no action non-self-overlapping, we can use a single clock variable for each action. And we know that there will be, at any point in time, there will be a single instance of that action running, so we can use a single clock variable to represent that. If we had also action self-overlapping, then we would need an unbounded, possibly an unbounded number of clock variables to represent that.
Thank you. Any other questions? If Paolo has...
Any idea to go with non-deterministic actions? I mean, there is all the work done by Alessandro and Andrea. With,
yeah, we didn't discuss that topic much, so I'm not too knowledgeable on that topic. For now.
Luciano, then.
Nice presentation, thank you. I couldn't resist to this question. So it looks to me that in your second approach, in the state, you are encoding some information about the future, no? Like the commitments and
yes.
the other parts. And while in the first approach, everything, all the information is encoded into the state variables. Mm-hmm. So, there is also some intermediate possibilities where some information about the future could be encoded into state variables. So it's not a 0-1 decision. You can decide to move things, to move information from the lambda into the state variable or into the matrix, as far as I understood. I mean, I didn't get the details, but I think that there is different possibility. Is it correct what I'm saying, or, I mean,
yeah, so...
does it have any consequence?
Yeah, so I don't know if I understood it completely, but yeah, so here in this approach, the future, the thing that we encode like in the future that you mentioned is in this lambda, which is the agenda on, like when we start a new action, we have all these events of that action that will need to be applied, and we insert them into this agenda lambda. Here in the NoXMV approach, what we do is we use these count variables, and we enforce that when we end the action, all the count variables must be set to true, and these count variables are set to true when you apply the corresponding event. So yeah, in this sense, so here in the NoXMV approach, we add these count variables, which are used to express that. Yeah, here in the CTP approach, we try to keep the planner as similar as possible to a previous planner that we started from, which was FTP. And the way that FTP explores the state space is very similar to this one. So it also has this classical part mu, the active conditions delta, and the agenda lambda, and only differs in the way they handle temporal constraints. So using difference bound matrices versus simple temporal networks. And the use of difference bound matrices allows us to get a decision procedure. So yeah, that was what we started from to build this algorithm. But yeah.
Yeah. So just to add a little bit on this one, Luciano. So I think you're totally right. It is possible to move some information from the to-do list that you have here to the state space. But actually having it in the to-do list, I will say that is better in general, because it allows me to use stronger heuristics for the search, because it's a more, let's say, clean representation of the future commitments, and instead encoding it in the state for me is more than a hack in order to use an existing technique. So I would argue that actually this way, so in which we have the entire information in the to-do list, is cleaner.
Yeah, I mean, I guess we have to move to the next presentation. And we thank again.
Thank you.
So, invite Mauro on stage. And while he prepares, I will introduce the title of the talk, which is Machine Learning for Utility Prediction in Argument-Based Computational Persuasion. I think there is also Ivan online. I don't know whether he wants to whether we can show up
because
him.
he was finishing a class.
Oh, okay.
So
okay.
I guess that he will.
And so, I mean, basically the floor is yours.
Sure.
And you can start the presentation.
Okay, so good morning to everyone. Thanks for the introduction. I'm Mauro D'Argoni, and I'm a researcher of the Process and Data Intelligence Research Unit of the Digital Healthcare Research Center. And this morning I will present work that has been done jointly with Ivan Donadello from the Free University of Bolzano, Anthony Hunter from the University College of London, and Stefano Teso from the University of Trento, titled Machine Learning for Utility Prediction in Argument-Based Computational Persuasion. After the introduction, I will give you some hints about what bipartisan theory is. Then I will present you which are the two machine learning algorithms that we developed for addressing our problem, and then I will show you which are the empirical results that we obtain from within our work. So let's start from the motivations of our work. We started from a concrete problem, came from the activities that we did during the last years concerning the design of coaching system or motivational system for persuading people on about adopting healthy lifestyles. This work has been done in collaboration with the local healthcare department. Maybe you were aware about the outcomes that we have concerning our engagement within the Trentino Salute 4.0 framework. And then by starting from this experience, we try to scale up this experience to build a more theoretical founded approach for designing automated persuasion systems, where the objective basically is to try to find which might be the most way for dialoguing with users in order to manage conversation for try to persuade or motivate them in changing their cognitive attitude concerning a specific topic. So not only related to healthy lifestyle, but can be applied to any kind of argument. Indeed, one of the most interesting aspects is that in this kind of systems, the system and the user have different utilities outcomes from a dialogue, because obviously when we are in a situation in which we have two or more actors that are dialoguing about a specific argument, every actor wants to try to bring the other actor towards its belief. Okay, and for addressing this problem, we decided to adopt a bi-party decision theory in order to use game theory for working within this setting. Why bi-party decision theory? Because this kind of theory is able to easily manage both the scenarios in which we have both a proponent and opponent that have to argue about the topic that is related to the scenario in which this kind of system can be deployed. But obviously, from the proponent aspect, since we know from the beginning which is the kind of system that we want to design, it would be quite easy to model which are the utilities that are expected from each dialogue action. But from the opponent perspectives, is quite hard to try to model which are all the possible utilities that can be associated with specific users, because the diversity of human being is very, very diverse, so it's very, very hard to manage these things. So the idea is to implement, to design a machine learning solution in order to try to predict, by starting from a set of data, which might be the utility of a specific user with respect to a specific argument. So our first research question was this one. But apart from obviously design an effective approach for predicting this utility, we also wanted to investigate also about which are the number of questions that we should ask for trying to understand which might be the optimal utility for that user. Why this? Because obviously when you have longer dialogues with users, this can affect obviously the level of engagement of the user, and also because we want to avoid to build a solution that needs to ask all possible questions to a user before to reach a conclusion. So also to understand and to infer which might be a feasible number of questions to perform is a challenge itself. From the literature perspective, obviously there have been several approaches that can be associated with the problem that we want to address, but that presents some limitation. For example, in general recommender systems, because if you want to persuade users to do something, you could decide also only to provide one single recommendation. But obviously, this recommendation only perform a one shot in trying to convince user and perform a specific action. That concerning a dialogue obviously is not a feasible solution because you need to manage more interactions with them, sort of multi-turn conversation. Then there were an evolution of recommender systems that were the conversational recommender systems that have the limitation of usually, as far as we know, not integrated very effective learning algorithms for trying to predict which might be the best possible outcome of the user that is using your system. Obviously, from the learning perspective, reinforcement learning approaches are the most similar ones to the one that we design, but they need, as all learning approaches, they need a lot of interactions before to start to become quite effective in interacting with the users. And then also planning systems and other probabilistic methods based on beliefs have been developed in this context, but their limit is that for them it's quite hard to represent effectively in the internal state all the user needs, because become different to predict one. So concerning bipartisan decision theory, which are the main elements? Basically, what we have, this kind of theory uses decision trees for modeling all possible dialogues. All possible dialogues means that obviously the set of arguments that are relevant with respect to a specific domain are finite, so we don't have a very huge number of arguments for each topic, so it is quite feasible to design all possible decision trees supporting all possible dialogues. And in these decision trees we have, apart from the leaf nodes, we have two different kind of nodes, decision nodes that are associated usually to the system, so to the automatic, to the AI component that is in charge of applying policies for selecting which might be the argument providing the highest outcome from the system perspective. And then we have the chance nodes that instead are used for representing user moves that, on the contrary, they have to, they are used for selecting which might be the most suitable argument for the user. In this kind of, within the bipartisan decisions theory, we applied the B-maximax policy that is a policy that aims to find which is the best compromise between the different utilities in order to manage conversation in order that both the proponent and the opponent are able to have a positive outcome from the dialogue. I put here an example of the sim dialog procedure, that is the name that we associated with our base approach. Here we have an example of a dialog concerning managing the conversation with the user that don't want to reduce the consumption of red meat. We have the set of arguments, and for each leaf node we have the left value that is the utility of the system, and then the right value is the utility of the user. At first step, obviously we have the decision node. That the decision node are the solid border squares, while the chance node are the dashed ones. For each decision node, they select which is the leaf with the highest utility from the system perspective. So they select which is the node, the leaf node, that has the highest left value. Because these are the two arguments that are considered by the system the most effective one from the system perspective. Then in the next action, since here we have the user that has to move, let's say it in this way, so he selects obviously the argument that has the most, the highest utility from the user perspective. And then this node is returned as a sort of outcome from the dialog. This way, we have the possibility of keeping the engagement of the user high from the system perspective, because obviously the motivation of continue interacting with the user is one of the most desirable insight that we want to have in order to being able to reach our goal from the from the system perspective. But at the same time, at each interaction, we want also to have the system that is able to have a small outcome as well, in order to move the cognitive attitude of the user towards the system one. Okay, so which are the approaches that we developed in our work? So let's start which are the ingredients of them. So we have a decision tree. Let's consider T as a decision tree, and then here we have the university of the universal set of opponents of the user utilities, in which which are all the user utilities that we can use for training our system. Then we have a vector containing which are the known utilities that are used by the system for building their learning solution. We limit this knowledge to the first E arguments in order that we call evidence, so this number, because we decide to use only a subset of these known utilities for predicting also the others. And then we use these elements for design, for keeping the sim dialog procedure shown in the previous slide with these two machine learning methods that are able to compute also the remaining utilities that we have in our vector. For measuring the effectiveness of the solution, we introduce a measure R that simply measures the difference between the outcome of the dialog procedure knowing all the utility values and the machine learning algorithms. And here, basically, this is I'm usually quite reluctant to put formulas in slides, but here I have to put it. We want to minimize as objective the difference between the two sim dialog procedures. The one equipped with the machine learning method and the normal one. Here in the original formula, we have also this penalty that considers also which is the length of the dialog, because in general, if we want to deploy it within a specific scenario, we need to take into account also which is the user effort in supporting, in replying all the questions. So let's start with the first approach that is called evidence as amount of information, where the automated persuasive system can access only a set of e-evidence. So the others are completely hidden to the algorithm. And based on the utilities that the algorithm knows, we build a regression model that is used for classifying the explicit utilities provided by a test user when he involved into the conversation, for predicting the remaining utilities that are originally hidden. And in this, for this model, we use a support vector regression solution, since demonstrated in the literature to be quite effective with respect to other solutions in working also with few data that can be also obviously the number of evidence that can be quite few. Instead, in the second one, second algorithm is called evidence as depth of search, in which the automated persuasive system is aware about all possible utilities value. But here we address the problem from different perspectives. So what we do at the beginning, we clusterize all the utility vectors within a number of clusters that is an hyperparameter of our approach, so we're not going into detail of this. And then from this cluster, we generate a set of decision tree. So we train a random forest model with a depth E that is considered our amount of evidence, in order to decide, in order to be able to classify each user with respect to each of the clusters that the algorithm detected. Once the user is classified with respect to the cluster, we use the explicit values we have in our decision tree as known utilities. And we use the centroid of the cluster that has been associated with the user for collecting the other utility values. We call this approach Kramer cluster and random forest linear regression. Then, concerning the result, so our aim is to compare, obviously, the scene dialog procedure and the one equipped with the machine learning algorithm. As case study, we worked with synthetic data. Why this? Because obviously it will be very, very hard to build a data set with 20,000 utility vectors collecting from, I mean, as well users from real. But the thing that we did is that we used, also a set of random decision tree associated with the synthetic data, but we also decided to use a realistic use case about a specific argument, in particular the consumption of red meat, in which we build a decision tree that has been extracted from the literature. So we used the real arguments for working on this. Then we generated the data set as I show in the next slide, and then we used a Manhattan distance simply for computing, which is the effectiveness of our approach. Concerning dataset generation, depending on the number of clusters that we decided to use in each simulation, we generated the centroids of the cluster, and then by applying Gaussian distribution, we generated a set of samples as much as we wanted to enlarge our dataset. And we did this both for the synthetic data and also for the dataset concerning the red meat use case, in which instead we we take into account also some more realistic features for generating this data. As baselines, we use 3 different baselines: random regression model for generating the missing utilities. Then we consider as missing utilities the average of such utilities in the training set, and then as another baseline we used the centroid of the clusters that have been estimated as a further baseline. At this website, you can download all the source code, the test data, and also all the supplementary material that we provided also at the conference. So, results on synthetic data. What we can observe here is on the x-axis, we have the amount of evidence that we provided at each step. So the more we go to the right, the more evidence are provided to the user. To the system. And what we can observe is that already with, let's consider for example this one, the rightest graph, already with 10% of the evidence the Kramer approach has an absolute error that is less than 1. In a scale of utilities values ranging from 1 to 11, we are able to achieve only with 10% of the utilities values provided to the user a very small error in understanding or in predicting which might be the utility of the user. And then what we can observe is that in general the Kramer approach from the beginning, from a very low number of evidence, already obtained a very interesting performance, and then this performance is kept, I mean, during the increase of the evidence. Instead, our SVR started with a higher error, and then it requires at least 50% of the evidence for obtaining the same effectiveness of the Kramer one. But obviously, by providing all the evidence, is able to have higher performance. A similar behavior has been observed also in the realistic use case in which our decision trees were not automatically generated, but has been built starting from the literature, in which obviously also here the Kramer approach obtains in general the best result with very few evidence. So for concluding this work, for concluding this presentation, this work represented, I mean, a first step towards the realization of this AI system for supporting this automated persuasive dialogue with users, and the use of bipartite decision theory demonstrated to be a feasible solution for addressing this. Obviously, it is interesting the integration of the machine learning approaches in this kind of scenarios, and then as future work there are a lot of things that can be done for improving existing algorithms, for designing new solutions, and then for deploying them into a real-world system. So thank you very much. If you have questions, and then if you want to contact also us offline, there is Ivan that was the principal investigator of this work, and then you can also instead talk to myself here in FBK.
Questions? Well, if not from the audience, I can start. So you basically explained your dialogue and your motivations in terms of healthy, let's say, lifestyles, and you had the objective of the low consumption of red meat. But if we talk about healthy lifestyles for real, it's much more than one objective. I mean, sure. So it's red meat, and then it's many other things. So how would this change your approach if you have, and the second thing is that you chose a specific, let's say, approach towards the utility, in the sense that you take this compromise in, let's say, having a good utility both for the system and for the user. So how sensitive it is to this policy, your approach, and whether something would change if we decide that the system has to win no matter what, for instance.
Okay, concerning the first question, obviously here there are different, I mean, if we consider, for example, that healthy lifestyle is composed by a set of many rules that have to be followed by user. In general, for arguing about each of these rule, it is necessary to build a separated decision tree in order to manage single conversations about a specific topic, because obviously if you enlarge, which is the objective of the dialogue, also the number of arguments increased as well, and then the effectiveness of the theories itself and also of the system that you want to train, I mean, decreases as well. So by addressing different rules or different guidelines, a different decision tree has to be thought for providing a more effective solution. Then concerning the sensitivity of the approach, it is something that I can answer you in the next month, because what we are trying to do right now is to test the different policies in understanding, I mean, for both the proponent and the opponent perspectives, in order to see which might, I mean, if the B maximax policy can be made more flexible by adopting different rules in understanding which may be the best. For example, not considering only the utility value of one actor or another one, but by trying to merge them in some way, for example, by applying harmonic meaning or geometric meaning, or other kind of solutions, for seeing if we would be able to to observe how the policy works also in other environments, because here we limited only to one strategy, actually.
Any other question?
My question is about the generation of synthetic data. How do you guarantee, because in other cases there are ways, for instance, if you generate a synthetic data for training in the vision, you can see that the movie is realistic or not, or you can have some constraint. In this case, how you do that? I wouldn't have data that are completely nonsense.
Indeed, here we have indeed two different test sets. The first one considering the realistic use case of red meat, in which by starting from the literature we would be able to describe the decision tree and to describe which might be possible utility values from the opponent perspective in different contexts. And then by starting from a set of, we design six different profiles of user by estimating together with domain experts which may be the utilities for each of the argument. And then based on them, we generated a larger number of samples that was in some way anyway related to this profile with small differences. Instead, for the other dataset, the biggest one, so the complete synthetic one, here it is also, the only negative feedback that we had also at review time during the conference, because obviously there is this risk. The fact that the dataset that we generated can contain not realistic data or things. This is an aspect that, anyway, fortunately, the reviewer understood that it was the only possibility for evaluating our approach. It is a thing that we still have to investigate in detail for understanding if there were some vectors or some instances that were not, correct with the scenario or not.
Yeah, I think we have to move to the next presentation, otherwise we will, and then, so we thank Mauro again.
Thank you.
And yeah, Sagar, yeah, it's you. So while you set up your computer, I will introduce your presentation, which is weighted model counting in FO2 with cardinality constraints and counting quantifiers, a closed form formula. Welcome.
I will take off the mask. Good morning, everyone. My name is Sagar Malhotra, and I'm here to present joint work with my advisor Luciano Serafini on weighted model counting in the two variable fragments of first-order logic. Let's first see what is model counting. So here I have a simple formula which says if you're a Trentino, you climb, okay? And I want to understand what is the model count of this formula. So I just go over all the models and I sum for each model, that is the model of this formula, a number 1. So I have 3 here. So that's the model count of this simple formula. So weighted model counting is, as the name suggests, weighted generalization of this problem. So for each proposition, you associate a weight for it occurring positively and negatively. And then you compute the models, okay, and for each model, you associate a weight which is product of the weights of the propositions occurring positively and negatively. So for here, for example here, the first model is Trentino true, Climber true. So Trentino 1, I go here, which is the weight of Trentino being true is 2.5, so I have a weight 2.5 here. And Climber being 1, I have a weight 0.5, and I have a weight 0.5 here, and I do a product of them. And then I sum the weights for all the models. So I do not want the red weight, but I want the rest of the weights. And the weighted model count here is 11.25. So, I mean, you may think, why is this an important problem? So basically, many problems can be cast into weighted model counting. It's essentially a assembly language for many problems. So I'm interested in probabilistic inference, where you can have a distribution on a lot of relational data expressed as logical structures. But then you can have neurosymbolic integration, which uses weighted model counting. You could test network reliability using weighted model counting. You can also go into some aspects of verification with weighted model counting. And then, for example, in social network analysis, you want to compute partition functions, which can be cast into weighted model counting. So now that we know weighted model counting is an important problem, so how do we solve it? So obviously, even testing satisfiability is intractable, and here we want to count a weighted sum for all the witnesses of a satisfiability problem. So it's completely intractable. So one approach is having heuristics and approximation algorithms, and the other approach is constraining your fragment. That is the approach that we will take here. So what we want is to identify a language where any query you do for model counting, that query is tractable. And when I say tractable, I mean polynomial time in the number of propositional variables that you have in the ground formula. I will come to the ground formula later. All right, so we will be focusing on weighted first order model counting. So let's say you have a first order logic formula, which is for all people, every x, if Trentino x is true, then Climber x is true as well. So this time you associate weights not to the individual's x, but to the predicates. So weight Trentino is 2.5 now. So if, let's say, in a model, I appear as Trentino false, so the model will contribute a weight of 5. I will contribute a weight of 5 in that model multiplicatively. On the other hand, if Luciano appears in that model, he will appear as Trentino true. So he will multiplicatively add the weight 2.5 to that model. So now we want to compute the weighted sum of all the models of this formula over n people, okay? And so the question here is, how do we do it? Can we do it tractably? And tractably for us is polynomial time here. So polynomial time with respect to n, okay? And this is our interest, especially, can we have a closed form formula? So can we write a nice formula which expresses this model count? And we want to do it for arbitrary queries. So we will dive into weighted model counting in the two variable fragment. So let's see what is the two variable fragment. So two variable fragment is just a fragment of first order logic where you have at most two variables, okay? And an example of such a language is given here. So you have a predicate fbk(x), which says whether x is an fbk or not. And then you have shaves xy, which says x shaves y, okay? So if you have a language like this, you can have a set of unary properties, which we call one types, okay? So what do I mean unary properties? They are properties of the individual. So they are property that I will realize only in a model, okay? So in a model, it is possible that I am not in FBK and I do not shave myself. I am not in FBK and I shave myself. I am in FBK, I do not shave myself, and I am in FBK, I shave myself. Okay, so the point is, any individual will realize exactly one of these properties, okay, and will have to realize at least one of these properties. So it's a XOR. So everyone has to have one of these properties, and there is no one which has none of these properties, and everyone has at least exactly one. All right, so I represent it like a graph, nodes here basically, on a graph with 6 domain constants. So each of these C1, C2, C3 can be seen as people, and the colors are the unary properties that I previously introduced. So here, I introduce a vector, a k vector, and which denotes the cardinalities of the colors. So k1 is 1 because there is only one node which is blue. K2 is 2 because there are 2 nodes which are green, and K3 is 1 because there is just one node which is red, and K4 is 2, similar argument. Now what I want is, I want to count the realizations of such possible node colorings fixing the cardinality. So what I mean by that is, if I go here, I have a new configuration, but the node colorings, cardinalities are the same. So I still have in this new coloring the same number of colorings. So I have same number of blue, green, orange, red and orange nodes, but the configuration has changed. So first I want to understand how many such configurations are possible, and that is given by a multinomial coefficient here, okay? And the semantics of this are given here. So 6 factorial is n factorial, so n is the number of domain constants here. And then I have a factorial each multiplicatively for each of the k1, k2, k3, k4, okay? And the number of such rearrangements is 180, okay? So now let's move to binary properties, okay? So binary properties could be that you shave somebody and somebody shaves. So I could shave Luciano and Luciano shaves me. We are really nice, student-advisor relationship. But then, you may not shave somebody and that person shaves you, and vice versa. And then you may not, you're completely enemy and you do not shave each other. So these properties are called two tables. Again, for the two tables, any pair of individuals can realize exactly one of the two tables and will realize only one of the two tables. So it's XOR again. So, and I represent the distribution of the two tables with edges and their colors, okay? So every edge here is a pairwise relation, and the color of the edge is the two table that the pairwise relation realizes, okay? So orange is representing 1, 2 table, purple is representing 1, 2 table, red is another 2 table, and it's a completely connected graph with the edge colors meaning the two tables. So when I add the one types, the unary properties, and the two tables, I have a complete model. All right, now I just know so far how do I count the number of ways of realizing the unary properties, but I do not know anything about two tables. So that is slightly more complicated, because what I will do now is I will try to pick a subgraph. And I pick the subgraph by picking two clusters of nodes of one color, individual color. So I pick the green ones and the orange ones now. And I have this. I just have these nodes, the green nodes and the orange nodes, but I picked all of them. I picked all the green nodes, I picked all the orange nodes. And I check all the possible pairings across them. So across here is important, because I do not check the pairing between C6 and C5 and C3 and C1. I check the pairings across them that they have. So I have the subgraph. I already know how to count the realization of the node colors. I want to understand the permutations between the edge colorings, okay? So what I do is I introduce another vector, which is H1, H2, H3, H4, and H1 here represents the number of red edges that I have. So I have two red edges. The number of teal edges that I have one teal edge, a color I learned from LaTeX. H3, I have an olive color edge, which is given here. So what I want to count is if I swapped the teal and the olive edge, I have a new configuration, and I want to count all such swappings. So that again is done by a multinomial coefficient here. So K2 into K4 is the number of pairings you do across green and orange, which is 2 into 2. Okay, so all such, and then you want to count the possible pairings, the possible colorings of the edges, given the color cardinality. So I fix that I have only two red edges. I only have one teal edge. I only have one olive edge, and I have no zero edge. And all such configurations are 6, given by the multinomial coefficient here. All right, so after all this hard work, I have a way of enumerating all the models. But obviously, this is just 2 to the n square something. Like, this is a very, I just wrote in a complicated manner, a very simple thing. But what I'm doing here is I'm counting all the models by distributing them first on the unary properties and then on the binary properties. But I still do not have any constraint. I do not have any formula so far. So now let's introduce some theory, some formula. So no one shaves themselves, okay? Everyone shaves each other, okay? And if you're an FBK, and you shave somebody else, okay, then that person is an FBK as well. All right, so now what does this formula do? This formula basically says that certain realizations of the graph will not be possible. And how does it check that? It says basically if one node is blue, another one is olive, and you have an orange edge between them, then that cannot be realized. Why? Because it represents this formula, which says not in FBK, do not shave yourself, not you are, the other one, the olive one is in FBK, and he does not shave himself, but they shave each other. It's eliminated by the third formula, okay? On the other hand, you could have allowed network motifs as well, many of them in fact. And this one is an allowed one. So you are in FBK, both of you, and you shave each other. All right? So what we do is we introduce an indicator variable for each such motif. So notice that this indicator variable, the number of these indicator variables are independent of the domain constants. It just depends on the formula. And we just multiply these indicator variables. So these indicator variables are 1 when the motif is allowed, when the constraint is allowed by the formula, and 0 otherwise. So now I'm going over all the unary properties, all the binary properties, but then I come here on this indicator variable and I check that is this configuration allowed or not for all possible configurations that they entail, which is given by the product. Okay, and even if one of them is not allowed, there will be a 0 in this product, and it just goes from the summation. All right, and you go over all possible such cardinalities to understand the model count of a formula. So in the paper, we are able to extend these arguments to existential quantification, and the principle that we use there is principle of inclusion-exclusion. Then you can extend this to cardinality constraints, where you may want to say that there are only at least 10 shaving relationships. And finally, you have counting quantifiers, which says that for all x, let's say there are at least 5 people you shave. Okay, so you could have many counting quantifiers, and you could have complicated queries which you want to count. All right, so again, having described everything, I just want to come back to the application aspect again. So basically, the key aspect that I'm interested in is learning and inference in relational models. And when I say relational models, they could be models which describe distribution on logical structures, but they could also be graphs. They could be any relational structure, and the probability are described on those structures. And in most of these problems, you can reduce it to weighted model counting. So for example, exponential random graphs are used in social network analysis, where you want to compute the partition function. And usually you would do MCMC, which also converges in exponential time. So you do not have any guarantees of actually what you are doing. So you do not know whether you really have a correct probability distribution or not. Whereas if your features in the exponential random graphs are in the 2-variable fragment, then you can cast that problem to weighted model counting. Then you have network reliability testing. So this one is actually done by Kuldeep S. Meal using propositional model counters. So they use approximate counters, but for simulation they used regular graphs, okay? And this problem scales so badly that even for small simulations, you are not able to have ground truth, okay? And first-order model counters can give you that ground truth for many such problems. Finally, there has been an application of model counting in Aaai MC. Aaai, I believe, is a software verification tool. And they used Aaai MC, a model counter in that, to figure out to quantify how much certain property is verified, is followed or not. And Aaai was already, I think, a higher order language. It's already a first order logic language. So if we are able to expand the fragments of first order logic that admit efficient counting, we can potentially, help software verification tools as well. So concluding, weighted model counting is an assembly language for a vast array of problems. But the key thing is that only first order logic languages admit polynomial time. Like only first order logic languages are known to admit polynomial time counting. We do not know any other logical structure which admits polynomial time counting exactly. So for DNF counting, you can have polynomial time counting approximately with guarantees, but no other structure admits exact counting in polynomial time. And our goal, we were here able to expand the fragments of model counting And we were able to do that in a combinatorial framework, providing closed form formulas for the model counting fragments that we addressed. Now we are working on consistency of probabilistic inference, which is completely motivated from our combinatorial treatment of the model counting problem, and hopefully approximate counting with guarantees. And on that note, I will finish the presentation. Thank you. I hope I was not.
Questions? Anybody? So, well, I don't know. If you want, otherwise I have a question. Okay. So I had a question, but it slipped out of my mind. I have another one. Oh yes, the first one was a curiosity in the sense that, I mean, my bad that I know very little of these. But you have a formula for counting the models,
Exactly. Yes.
Not for generating them, or can you use your diagrams also for generating the actual models and their weights?
In first-order logic, I think you can also generate those models, yes. In first-order logic, though.
Okay.
So I would not, yes.
In your fragment?
In my fragment, yes, yes.
Okay. And the second one is concerning your future works. I mean, I can see why your solution seems tied to the specific fragment in the sense that you use your unary and binary predicates to build the graph structure.
Right.
So if you had to go beyond that, any idea? Because you have to restart, I mean, can you use what you've done or you have to use different approaches?
Okay, so I will, so it's a bit, sorry, I should maybe emphasize, yeah, so we start with two variables, yes, but for example, this formula already is only expressible with many variables in reality. But you are right, if I have a formula, let's say as simple as transitivity, okay, you cannot count in efficiently. And that's why I like this problem a lot, because it's like you have simple statements and you cannot, like it scales really badly. If you try to run any even exact model counter, so for example, I'm sure transitivity, you will not be able to count for 10 domain constants. So yeah, I mean, it's a valid point, and I know we are.
It was just, obviously it doesn't change what you've done. It was just. Yeah. Any other question?
I'm sure you know the work by Luciano on logic tensor network.
Yes,
right?
yes.
Which is the relation of the two? Because in a certain sense, Luciano made this assumption to have fuzzy logic that I believe is a very realistic and not well-motivated assumption, as something that in some way constrains or the neural networks. Here you start from this kind of frameworks that are much more interesting at the symbolic level, I believe. So is there any relation with or no? I mean, in this way of
I do not know so much
logic
about
and neural networks in some way.
So, okay, I do not know so much about logic tensor network, but I think there the problem is similar to a MaxSat, if I'm not wrong, there. And on the other hand, if you go on frameworks like ProbLog, for example, where it is probabilistic logic programming, there the problem again reduces to weighted model counting. And I do not know how you would port a logic tensor network sort of situation to model counting, because there you are, I think, trying to do a MaxSat type of a thing, I believe. I'm not so sure about it, yes. I don't know. I mean, Luciano is expert on both, so he would know.
Luciano's is the relation.
Yes.
So anyway, I think we have, unfortunately, to move to the next session. So I would thank Sagar and all the speakers, and I will leave the floor to Oliviero.
Hello. I think we are celebrating now Luciano. I should start with a quotation by my favorite philosopher, which is Groucho Marx. And he said, I wouldn't want something like, I wouldn't want to be fellow of an association that accepts FBK people among its fellow. I'm mentioning this because also Paolo is a fellow of Aaai. Well, I was myself, and I'm very pleased that recently also Luciano has been appointed as fellow. And he certainly deserved that. I should say that I first met Luciano when we were basically setting up FBK, IRST, what it's called. It was called at the time. And I remember very well that I met Annalisa Marcia, who was a professor of logics, and she was my professor of logic. She was very young, I don't know. But she was my professor of logics, mathematical logics, well, many years before, 10 years before, 12 years before, 14 years before in Florence. And at that point, she was professor here in Trento. And if I remember correctly, Luciano had the laurea in Milan, right? And she was your supervisor from here. And she was enthusiastic about Luciano. So indeed, I learned about his work, and soon after he was hired temporarily and then for good here. And I think it was one of the many very good choices that IRST made at the beginning of its history. And now you heard that Luciano is part of one of the latest successes of FBK in the previous paper. And all his history is really a history of being at the foreground, not only pioneering, but then going on also with ever novel ideas and contributions. So starting from his work on computational logic, where he contributed with a lot of important things, important papers, going on up to recent times when he tries to integrate logic-based approach and, so to say, probability-based approaches, from several different aspects, with a serious, one of the few very serious efforts at integration, with contribution different themes, including the collaboration with Paolo, as far as I know, on themes regarding reasoning for planning and so on. Knowledge representation, of course. And so I think I think that we at FBK should also commend Luciano for being so active in trying to put people together and discussing novel aspects of AI, also from different points of view, irrespective from ideological positions. And I think this is very important because, as we know, AI is a collection of different themes, and sometimes we try to integrate those themes and finding a common ground, but most time we do not. It has become a very technical and also sometimes very narrowly focused area. So Luciano is really a fundamental resource for us. Should we have the possibility, we should be really a fellow of FBK in the first place, forever. So Luciano, please say something about it.
I was really emotionated by this. I took some note because otherwise, well, thank you to everybody. I can say only few things. I also go back to the past, to the 88, where I was doing my master thesis by Professor Marcia at the Department of Mathematics. And I remember Oliviero and the group of natural language he was creating. And I clearly remember they invited me to give a seminar about knowledge and beliefs, things like this. And I remember very well in the room, which was in the old building, there were Carlos Traparava, there were Bernardo Magnini, there were Oliviero, and there were Enrico Franconi as well, our former colleague. And that was my first step into FBK. At that time it was called Istituto Trentino di Cultura, IRST. And so since then, my career, my research, essentially is divided I'm here since like about 30 years, a little bit more, but it's 10 years plus 10 years plus 10 years. So in the first 10 years, I worked very hard into a topic that was the logic of context, where knowledge was spread in different places. And this was much before the advent of the semantic web. Okay, so this was in between 88 and the 2000. And this was under the beginning, especially under the supervision of Fausto Giunchiglia, who is now a professor at university. Then in the second time, then I get into the semantic web. So I saw semantic web as a real concrete architecture where this idea of multi-context could be realized. And indeed it was. And it was like, I was really lucky in thinking to the semantic web, to the multi-context before the semantic web. It was really just a chance, something that you get by chance, not planned. And okay, so during the first decade of the 2000, I just working on semantic web, ontology matching, integration of heterogeneous databases and things like this. So you have. Then in the 2010, around that, I start to get a little bit say, okay, knowledge representation, logic is very nice, but I need something more. I need numbers. I need to work with numbers. And I think it's a good idea to integrate numbers, probabilities, neural networks and things like this into the logic part. And we start with, I remember one project, it was called with a very strange acronym, Copylosk, with a K, I don't know, at the beginning or at the end, I can't remember. So, and the idea of that project in 2010 was to integrate logic and statistical and numeric reasoning. And I remember we give a presentation about this project here. And since then, clearly I keep on working on my other stuff, but I investigate more on the integration of learning and reasoning. And as you know, now integrating learning, reasoning, symbolic, sub-symbolic is one of the main topics. So that was my research that I've done. It was really a pleasure. I've really worked. And I cannot avoid in making thanks to people, to institutions, and to communities. So there are three things. So let me start with the people. And I go historically here. I really want to thank Fausto. Fausto, he was my initiator. He initiated me to research. I really want to thank Paolo. Paolo, he was my the person that makes me a mature researcher, that put me in the position and give me the possibility to develop the full potential that I had. Whatever it was, I mean, it was really, I was really thankful for this. I want to thank FBK and IRST because they give me the environment and the resources, the money to do this job. And I want to thank all my collaborators in the scientific work that were so patient to work with me and to support, not support, but supportare, I don't know in English, my bad characters and so on. Last but not least, I really want to thank Chiara, because if now I get the award, is because she was promoting and she was spronare, non so come si dice, me in going in this direction. So thank you to everybody, and thank you.
Why don't you say 2 words about your view of the future?
Oh.
Whatever you want to say.
So, view of the future. I wear very thick glasses, so you can't think that I see very well the future. But I don't know what to say. I mean, I think what so I can say what I feel. I mean, my feeling is that we have to face first hard problems and principled problems, not just data set optimization. Okay? And the hard problem for the time being, I think, is the integration, but not only of symbolics, sub-symbolics, and things like this, but the integration of the different areas of artificial intelligence. Interaction, action, learning, reasoning. All these technologies has been developed in a very, so we have really a lot of tools that do very well a very specific task, that solve very well a specific task. But if we go a little bit higher, out of the specific task, we are lost. So we are lost because if you make the task a little bit more general, a little bit not very well crafted, then you need a little bit of knowledge, you need some interaction, you need much more combination of technologies. And that's not just a technological integration, but is an integration of theories. Okay, so behind all these approaches, in artificial intelligence, neural nets, logics, all these things, there are always good theories. So when you do this type of integration, it's not only that you have to integrate the last platform that do Theano or whatever that solve some problems, but you have to integrate the theories. You have to understand how the two theory interacts and they overlaps possibly. So that's my feeling. That's what I would like to do in the next. And what I think is a good direction to go from the research point of view. I don't know if I answered.
Now, Luciano, for the immediate future, has to take the train. I think we go on immediately. We skip the break, but I would like to use the PowerPoint for a second. And I don't know where is the connection. This one? Okay. Okay. I would like to thank Chiara. I would like to thank Chiara again for organizing this workshop. It's really wonderful, and also for me, it is also an occasion for thinking back about the past. In fact, it has been recalled how there was this extraordinary event in 2001. I should say also that this is special. I will come back to this, but I think that there was, I will double check then, but I think that there was one Aaai or Aaai when we had altogether 7 papers. This is what I recall, but I will let you know. Anyway, in 2001, Aaai, Seattle, there was this extraordinary event. The extraordinary event being that there was one session, 3 papers in a session, all the session by ITC Hearst people. All the authors were ours. So afterwards, when we knew this, I was director at the time, and I said, well, we must replicate this here, and this room was full of people. There were, as things are among researchers, I remember that there were some people from other sections who said, why those and not us? But this was absolutely extraordinary. And for us, it was really a factor of great prestige, also big pleasure. So this was the session. And as you see, in this session, there were repetitions. So most authors are authors of 2 papers. And what else can we observe? 3 of the authors have become director at FBK. One has become a great cyclist, as far as I know. I don't know anything else about Per Giorgio. And the drummer. Okay. So, for the young ones, being author of important papers may lead you to a very important, successful career, like being a cyclist and a drummer. And then, well, one has moved to the university. I don't know. I hope it was the best choice for him, but recently. So, very good. And so, of course, Aaai 2001 is remembered for this. There was also another speaker you may have heard of, this guy, who gave an address at that Aaai. By the way, speaking highly about the prospects of AI. And it was a bit before the, how should we call it, the AI summer or whatever. I mean, the moment in which everyone is emphasizing AI. Yeah. So, now celebration. second celebration after Luciano. We talk about the most important paper of AAAI 2006, Boston, and which was delivered by Carlo Straparava together with Rada Michalcea, who's also a friend of FBK, and Carly, who was, I think, a student of Rada at the time. This is the most widely mentioned AAAI 06 paper, right? So a classic paper and an honorable mention. I should say that Carlo did all the important and serious work with other people. At the time, there was also another paper that we had together, but on a dishonorable topic, humor. By the way, I should also, now for the old ones, I should also remember another rich guy, which was probably 2005. We had a paper on which was called Getting Serious About Computational Humor, at each guy, Carlo and myself. And and each guy was in Acapulco. But wasn't it only in Acapulco? The day was exactly the day of our paper, or the start of the conference was exactly Ferragosto, 15th of August, which is the highest holiday in Italy. Everybody is on vacation. And so I had to ask to the director of services here, famous person called Tonini, and I said, we must go on Ferragosto, paid by the organization. We must go to for Ferragosto to Acapulco to present a paper about humor. But anyway, after some discussion, we managed to go. But I'm mentioning this thing, but Carlo was really instead a very serious person who made a very important contribution that correctly is, I go back to that one, that is a reference, because at those times it wasn't so common to think in the ways in which the paper introduces, and also Carlo has gone on with his work, and not only is honorable for the mention, but is honorable for what he does today. So, Carlo, you may want to say something.
Okay, so I can put off the mask. Yes, what can I say? So, thank you, Oliviero, for the introduction, And I just prepared two slides to sum up the genesis of so it was quite unexpected we received the prize. At that time, the requirement that Aaai put for getting this award is in this list. So it sounds incredible. So started a new research area, lead to important application, okay, answer long-standing questions, major, and you can see here, okay, okay, in this you can have a list of a Hall of Fame of everybody that got the and this is the citation of the paper. So I'm not one that go every month to say and so sometimes that we received the award, I checked what happened. It was the most cited publication of that edition, and even in these years, get a lot of citation. And it is interesting that, and this happens also for other papers that highly cited. At the beginning, almost nobody cites. So it's very slow, very few mentions. So even in the research community, there is an inertia in this. And by the way, this is why I think it's so difficult to set up a research institute, because even if you have a lot of great researchers, to get achievement, it is a matter of 5 years, 4 years, 5 years. So, we live in a world, in a very quick world, so we have to run, but in fact, the things in the research move slowly, okay? In the research community. In the industrial, even slower, okay? Even slower. Our paper in particular, so it was about text-to-text similarity. It developed some technique to check the similarity, text-to-text similarity. It was one of the first papers moving beyond the word-to-word similarity. And, you know, at that time, nowadays, for example, embedding are very popular, is what we use. But at that time, having a vector that represents like a summary of the context of the word, the text around the word, is not so used. Nowadays, it's like to say that a car has a wheel, okay? But at that time, no. At that time, no. And using this kind of representation boost any task. And so the paper facilitated a lot of tasks and application. The knowledge graph, the affective computing, which was another field that me and Rada started. But also used in our work of humor. The last work about catching news title in IJK paper and so on. Text plagiarism, educational application, and a list of famous papers that cite ours. So I have looked this as a very important. So it was an honor to have citation from this kind, but this is the front stage, right? And everything is linear, is clear. Oh, okay, you write a good paper, you get a lot of citation. But the fact that you don't know in advance what's happened all this. In other words, the suggestions that I can give to especially to young researchers for the, let's call a recipe for getting an achievement, is explore what you really like. So it's simple, but I thought a lot about the why why we got so you have to explore what you think is valuable and worthwhile. Okay, at the time on which you write, you don't know the importance. So you suspect that is okay. You suspect that is, and probably working with great colleagues. This is the key. So with Rada, we wrote a lot of nice paper. With Oliviero, Oliviero mentioned other paper of AAAI, of IJK about humor, and this is another important point. Working with great colleagues that share your vision. So, there are so many people I have to thank that it is impossible to have a list. So I'm not an easy person, so I am very stubborn in following some, and so I don't know. I like to work with my colleague. I don't know if my colleague like to work with me, but I think that the results are good. I don't know if Rada connect. Oh, Rada, you are here. You want to say something about? Okay.
Sure. Just that I very much agree with what you said. That doing what you like, working with great people is the recipe.
Yes,
and
yes. And
I personally have mixed feelings about getting test of time awards. I think young researchers do not get test of time awards. So it also says something about the stage we are in. But it's also nice feeling to look back at work that we've done a while back. And still recalling the way we went about it and how we've been thinking, and just the back and forth on what would be the interesting questions to ask and all that. I think that's always exciting. It was exciting all those years ago, and it's still exciting now, looking back.
Okay, so, okay, thank everybody again, and of course, I wish you a lot of achievement like this. I hope you get the same satisfaction. Okay.
Okay, I think we can.
Ciao, Rada.
Thank you.
Ciao.
Thank you, Carlo. I don't know whether Oliviero, you want to conclude. So thank you, everybody. Let's hope, yeah, this is a good stimulus for the future. But for a moment, I think we should also learn to enjoy what we have done now. Because, I mean, I always feel we are looking forward, looking to the next thing. But perhaps for at least 10 minutes, we should simply enjoy what we have done and be proud of ourselves. So have a good day, everybody.
Really, thank you.